have any good examples to help understand or help explain to a new calculus student why the derivative and the integral are, you know, more or less inverses of one another, or why they kind of undo one another?
Oh, why do they undo one another?
Yeah,
Um,
because it doesn't seem obvious at first when you learn like a derivative is the slope and the integral is the area. It seems not completely intuitive that the integral of the derivative and vice versa, you get the original function.
yeah, that's a tricky one. Um, I mean, we like I can go through why they're inverses of each other, right? It's because when you go to add up the area under a curve and you attempt to do it with an infinite number of little tiny rectangles, they create a telescoping series in which they continually cancel with each other as long as you're talking about the slope of that, whatever the antiderivative is of that function, right? Meaning you're talking about the function itself as the slope of some other function, then you
Uh-huh.
can get them to telescope and cancel, and that gives you the fundamental theorem of calculus, which is that the antiderivative gives you the area underneath the curve, right? So
Hmm.
like we can go through the steps that make that happen. Like there's a very rigorous proof of why that is the case, right? But it gets much more complicated than that. So
Yeah,
um,
I'm trying to find a way to help explain to some of my students, like to give them
mm-hmm.
they're not going to be going through a rigorous proof. I'm just trying to help them like
Mm-hmm.
because a lot of them are confused at first because it just doesn't seem obvious that the slope and the areas are related to each other in this way. So, yeah, I was
Mm-hmm.
just curious if anything came to mind. I'm always trying to find new little
Yeah,
explanations.
yeah. Um, yeah, the slope and the area are related to each other. Yeah, that's true. Yeah.
It's one of those things I feel like after doing calculus for so long, you kind of start to take it for granted. But then I have a student ask, like, why is this the case? I'm like, uh, wait, yeah, good, intuitively, it doesn't feel obvious.
Yeah, it's not obvious, especially when you start doing Calc 3 stuff and you start doing it in a bunch of different ways, right? Cuz you start doing like, well, here's a parameterized curve. Let's find the length of it, Well, we're just going to pretend that these are infinitely small and then we're just going to do the
Hmm.
integral because that's like obviously what anyone would do, right? And,
Hmm.
it's somewhat unintuitive, right? Um but yeah, the the reason, yeah, the only way I can think of is just thinking in terms of the proof, right? So it's like, okay, I have a rectangle, then I get a rectangle, then I get a rectangle, right? And they don't have to be like perfect approximations or whatever, right? But so you're trying to integrate, right? The function. And so this means to add up all the, infinitely small rectangles. And so because the rectangles are infinitely small, um, then uh, then we're going to think in terms of the slope, right? So what is it that this typically translates into? It's like the sum of fxn plus 1 minus f of xn, and then you
Hmm.
have the width of the interval, and
Uh-huh.
then this is going to be the height, and then you times it by the width, right? And that's always going to be what it is because this is what the height is going to be, right? Um,
Oh, I see. Okay, yeah, and then that first term is the slope, and then when you take the limit, that becomes the derivative.
Yeah, so this is like approximately the height, but you
Uh-huh.
have to be, and then this is approximately the length. And so the hand wavy part is you're like, well, they're infinitely small rectangles. So they're infinitely small. I mean, they're not infinitely small, so they're not zero, but they're infinitely small.
Hmm.
And so we have the height and then we have the length. And so each of these is going to get added up. And so that this intuitively makes sense. Okay, we have the height, we have the length. It's just you have to convince the person that this is the actual height, right? Um, and then everything just is automatic, right? These cancel, and then you have a telescoping sum, and so that becomes f of f prime. Oh, forgot to put the prime there. F prime of b minus f prime of a, right?
Hmm.
And so that's the tricky part is you have to convince someone that that's approximately the height of what a rectangle looks like. Like if I have a curve and then I have a rectangle, right? Then approximately the height is, and I have a base, which we'll call delta x, then approximately the height is f prime of xn plus 1. Um, am I doing it backwards? Oh, crap, it's the other way. You have to put the prime there.
Yeah, because you have to do the
I did it.
antiderivatives there.
Yeah,
Yeah.
my bad. My bad. The prime goes there. See, so you're integrating a function's derivative, and so you have to
Uh-huh.
you have to you have to convince someone. Okay, this is f prime. This is f prime. Here's a rectangle of f prime. Then the
Hmm.
height of that thing is f of xn minus f of xn divided by delta x. And so that this is the tricky part that you have to
Oh,
explain
okay.
that
Yeah,
that's
yeah,
the
yeah.
height. So this is about the height is when I do this, right? And the reason is because, well, we're effectively the height is going to be the slope because f prime
Uh-huh.
is the slope, right? So f prime is the slope, and so we expect this height to be the slope, right? And this is how you would calculate the
Uh-huh.
slope.
Yeah, just change in
Yeah.
y over change in x.
Yes. Yeah.
Okay. Okay, cool.
Yeah. Mm-mm. Oh, I gotta.
You I was just recently looking over it's like Gabriel's horn or whatever, the infinite surface area but finite volume.
Oh.
Um, and I was looking at the integral, the arc length integral,
Mm-hmm.
and there's that little manipulation that has to be done to make sure that I guess the heart of my question is why can only some sums, Riemann sums, be turned into integrals?
Why can only some Riemann sums be turned into integrals?
Or I guess why I think all Riemann sums can be turned into integrals, but not you can't turn any sum into an integral. It has to be of a certain form.
Sure. Well, so a an integral is always involving a function, right?
Hmm.
So like the integral from, I mean the integral of h of t, assuming we split it up into an infinite number of pieces, is always h of some point in the middle, right? For each n, times
Mm.
by the length of that interval, right? So like that's
Some point in the middle. What? Why that part?
why the sum point in the middle. What do you mean? So
Yeah, that piece. I don't fully understand what that is.
so the Riemann sum is that you are allowed to pick the number between the points arbitrarily, and that the limit is the same for any choice. So
Pick the number between the points arbitrarily.
yeah,
Okay.
so the definition of the Riemann sum is that if I take the limit as what is called the mesh of any collection of points. So we'll call them. I'll just make it just throw in as much notation as possible. So we want that to go to 0. So this symbol is representing the mesh. So we're going to take any set of points between A and B, any set of points. I want the mesh of it to go to 0. So the mesh is the distance between the points. So like if I have
Uh-huh.
0 and 1, and then I pick them evenly, right? And let's say these are 1, 2, 3, 4, 5, 6, 7, 8. They're eighths, right? Then the mesh of these points, 0, 1, 0, 1 eighth, 2 eighth,
Hmm.
all the way up to 1. So that set, call it T, the mesh of T is 1 eighth because it's the
Uh-huh.
greatest distance that you see, right? Well,
Okay.
the NET, you could pick these arbitrarily. They don't have to be evenly spaced. They can be big, small, tiny, whatever. It's just you want the mesh to go to 0. So as the mesh goes to 0, meaning that as your rectangles get tinier and tinier, then you want the limit of this to be some fixed value no matter what points in between the intervals you pick. So the Tn stars can be anything in between, right? You could put when you're looking at 0 to 1 over 8, then T1 over 8, or T1, I guess, T1 star, it could be, you know, anything in between here. It could be 0 point, 0001, right?
Uh-huh.
That's in between the two. And so that would be an example of a point that's picked between the two, right?
Okay. Okay, I see.
Yeah.
And yeah.
So the formal way that the Riemann sum is defined is for all possible partitions of the interval and all possible selections within the partitions, the limit as the mesh over those things goes to 0 should exist. As long as the
Uh-huh.
limit of the mesh going to 0 of all those possible choices, this sum converges to some number, then that number is defined to be the integral, right?
Okay.
Yeah.